terima kasih atas kehadirannya. Saya tidak menyangka cukup banyak ya, tadinya jadi banyak yang interest. Thank you very much for coming in this Wednesday seminar. Usually this is done every week, yeah. And today we have guests from Inha University, Korea, Professor Hyun-Chul Kim. He's actually my colleagues or my collaborator in my research. I met him, I think, more than 10 years ago. Yeah, actually, he got his PhD from Bonn University in 1993. I got my PhD in Mainz University in 1996. Yeah, but he got his master degree in 1990. Yeah, 1990. I didn't have master degree. Yeah, I don't know why. Yeah, I got my bachelor degree in 1980, 88. Well, more or less we are in the same age, yeah. But at that time we didn't meet in Germany, but we met several times in Japan and in Korea. So he got his bachelor degree from Inha University, where he is now a full professor there for since a long time ago. Now I think he will retire in about 4 years. So he told me that, yeah, I'm really sorry, he no longer accepts students. But for some discussion, maybe it's okay. Yeah. Okay. Uh, he's going to talk about chiral effective theory for the structure of the nucleon, which is for me very interesting topics. Yeah, and he's expert in the chiral solitons model. You can ask about soliton models, also about skyrmion. Yeah. Okay, please.
Thank you very much. So this is my second visit in Indonesia. So first time I visited in 1990, I know 2008, so almost 16 years ago, where the international conference was held in, yeah, University of Indonesia. So then I organized the same conference after 3 years. So I know Terry for a long time. Even I think he probably forgot it, but he just told me that I think in 1993 or 1994, we exchanged an email because he asked me some data from my results. So he used it. So I remember it. Thank you. Yeah. Thank you very much for a nice introduction. So I prepared, because I was told that I have to give kind of lectures for 2 hours. So I prepared a lot, but I spent 2 days. Then I realized this is 100 pages, exactly 100 pages, but I'm not going to talk about all these pages, but some pages I'll go very quickly. But the first one third of my talk is prepared in particular for students. So you probably can follow the beginning of this one third. And then maybe last it will be more specialized. And maybe some of you will be interested, but nevertheless, and maybe the last part is really specialized one. So maybe you simply, watch what those people in hadron physics are doing. Okay, let me go on. Okay, the title of today's talk is Chiral Effective Theory for the Structure of the Nucleon. So another name is the chiral quark soliton model, but as far as you stay in SU2, even we can call it the theory because you have no free parameter. Everything was determined in the context of QCD. So you probably know QCD. QCD is quantum chromodynamics, which is the underlying theory for the strong interactions. So, which means that if you are really interested in describing hadrons and related phenomena, then it's better to be grounded on QCD. But of course, since QCD is so difficult, we cannot solve it, except for the lattice QCD. So we need we need to build up some models or some theories based on that, a kind of effective theory. That's why I call it chiral effective theory. Chiral, I'll soon explain what it means. So nevertheless, let me briefly summarize some history about the nucleon. I think you learned in modern physics, Rutherford found can I have some pointer or some sticks? Maybe if you have a sticks, it will be better. I prefer the more classical way. I prefer. Okay, let me continue. So I think you learned the Geiger-Masten experiment. Then what they have used is the radioactive material where you can get some which decays into alpha and the daughter nucleus. Then by using this alpha, you can study some another isotope or some nucleus. So they simply the shoot this alpha to the gold foil. Then they try to measure some the cross section. So I think you learned this experiment in at school. Then the do you know why the Rutherford did such an experiment? Because he was a professor in McGill University. There he used some alpha scattering experiment. Then he realized that alpha is slightly bent over. So then he got some idea. So when he got a position in Manchester University, then there was a student that must be just 22 years old, and Hans Geiger is a German physicist who is really great experimentalist. Then one day, Geiger came to Rutherford and asked, we have a new student, Masten, and maybe he is looking for some subject. So Rutherford suggested that experiment. That's why it is called Rutherford scattering. Also, he precisely analyzed the result in a correct way. Of course, at that time, they don't have any good detectors. So what they have is two important things. One is bare eyes, and the second one is microscope. So by looking into the microscope, then whenever alpha particle hits this gold foil, then you can see here some the fluorescent screen. So you can see very small some flare. So you simply count it. So if you read their paper, the method of experiment is well described. Which is very interesting. I think I strongly recommend you to read the related paper. The first thing before you measure, you have to go into the very dark room. You have to stay there for 30 minutes until your eyes get used to this dark, a kind of dark mode. So then you can, but you cannot also measure more than 30 minutes per day because your eyes are tired, so you can make easily mistake. So every day you are allowed to measure only 30 minutes. Then even the eyes are so important. You always have to keep your eyes very in a good condition. So there is some anecdotes that the Geiger and Masten somehow traveled to go to some workshop. Then Masten just looked. He was in the train that he simply looked outside with his head. Then Geiger simply took him inside because saying that you have to keep your eyes safely. Because if somebody smokes, these small things will hurt your heart, the eyes, which means you simply break your detectors, right? So eyes are so important. Then they got very interesting results because whenever alpha particle hits this gold foil 5,000 or 6,000 times, then suddenly one alpha will scatter in the backward direction. So Geiger reported this result, and Rutherford reacted as follows. It was almost as incredible as if you fired 15-inch shell at a piece of tissue paper, and it came back and hit you. This was really surprising result. So he really spent for a whole year. Then he came up with one great idea. So in the center of the atom, there is kind of nucleus. Nucleus was taken from biology. In the cell, in the middle of the cell, you have a kind of nucleus. So he learned it from biology, then he took the name nucleus and he christened this as nucleus. Nowadays we call it nucleus. Nucleus consists of proton and neutron. Neutron was found much later in 1932 by one of his students, James Chadwick. So nucleus was born. So I would call it this is nucleon 1.0 because nucleon is considered as a fundamental particle, no structure. Okay? The proton is a fundamental one. And also he named the proton in 1920. So this is the proton, the simplest nucleus. This is a hydrogen atom, which was pictured in 2013. So looks like really S-wave, the wave function. So here is the proton. And 1920, the Rutherford called proton. But if you take a look at this paper by Mason in 1921, actually Mason called the simplest nucleus of the hydrogen atom as the baron. Taken the word in Greek, the baros. Baros means heavy. So he called it baron. But then Rutherford said, no, you should not call it baron because I already named it. So which you can find here in the footnote by Professor Rutherford. And you really can see somewhere the name baron suggested by Professor Mason was mentioned, but was considered unsuitable on account of the existing variety of meanings. Finally, the name proton met with general approval because he suggested in 1920 here Cardiff workshop. He called it the proton. So also the Rutherford name the proton. The proton is the simplest particle, and also he explained why he tried to call it the proton because this is kind of protyle given by Prout because he somehow showed the respect by calling it proton, the name Prout, and not only that, but also the name proton means the first particle from the Greek. So it is a very good name. So then now let's change nucleon 2.0. So from nucleon 1.0, the proton is considered as a fundamental particle. But in 1933, the Otto Stern and the Robert Frisch and Ismail Esterman, these three experimentalists, actually Otto Stern, you know the Stern-Gerlach experiment in quantum mechanics. He was a real expert and somehow kind of founder of molecular beam experiment. He was almost the first person who did the experiment using the molecular beam. So they measured the magnetic dipole moment of the proton to be 2.5, and mu-n is nuclear magnetism. And this is much larger than 1, which means the proton must have a structure. But of course, nobody knows how it looks like. But I think when I talked about this story, then Terry he told me about very interesting anecdote. When the Otto Stearman gave a talk, then there was a Wolfgang Pauli. Of course, Wolfgang Pauli, every physicist know who he is. Pauli exclusion principle, and also Pauli term in the Schrödinger equation. And neutrinos. He contributed a lot to physics, but all his contribution was cancelled by what he said. So contribution of Pauli to physics is zero because he always against some new idea. Antiparticle, no, such a particle doesn't exist. And when Otto Sterman said this is 2.5, no, you absolutely made bullshit mistake because it should be equal to 1. But keep in mind, he introduced Pauli term, the magnetic interaction, in the Schrödinger equation. Then suddenly, and also we call it F2 form factor as a Pauli form factor. This anomalous magnetic moment. But nevertheless, Pauli insisted it should be equal to 1. But no, he was wrong because they were right because 2.5, now the present data tells us the magnetic moment of the proton, magnetic dipole moment of the proton is 2.79. So 2.5 is very close to 2.79. But there is also a very sad story behind here because it is measured in 1933. Then you see in 1933, Adolf Hitler seized the power in the beginning of the March 1933. Then he introduced some very harsh regulation against Jewish people. So he was in Hamburg University, then professors will be one by one kicked out. Jewish professors were kicked out, all the scientists were kicked out. But he's so famous, so he still keeps the position till August. Then again, Otto Stern and Esterman were finally resigned. No, Otto Frisch is from I think he left for already Niels Bohr Institute. Then he wrote the final paper from Otto Sternman's group. It is German work. Let me explain what it means. You see here, they could carry out better experiment. However, because of the situation outside, we cannot perform experiment anymore. This is very sad. It is written in the final, this is actually final paragraph, which was written by Frisch in that paper. So somehow all this result, physical result, you cannot ignore also this history, right? So somehow very sad history behind it. So anyway, the proton magnetic moment already implies that the proton must have some structure. Okay, and then in 1955, 56, actually he carried out that experiment in 1954 to 1956. There's Robert Hofstadter, of course, he received the Nobel Prize. And Otto Stern also received the Nobel Prize. And he carried out experiment using Mach 3 electron accelerator at Stanford University before the SLAC was founded. Then he used also scintillator, the NAI and the little bit thallium. So actually he developed that scintillator. This was also part of the reason why he received the Nobel Prize. When he measured electron-proton last scattering, then he actually drew the data for differential cross-section. Assuming that the proton is structureless particle, then you have to follow that line. This is kind of so-called the Mott scattering, the cross-section, assuming that the electric charge radius and also magnetic radius equal to 0. Then the result the experimental data should follow that if the proton is a fundamental particle. But on the other hand, the real data looks like this. Okay. So even he measured the charge radius of protons around 0.81. This is RMS value, which is very close to what you know nowadays. Of course, now this charge radius is also a big issue because some atomic physics and the particle physics give different results. But now their discrepancy is getting smaller and smaller. Maybe within few years, maybe we'll make some clear conclusion of the size of the proton. The size of the proton is also still open issue. Okay, then they came up with great idea. So if you take a look at Yannis' paper, then those in 1950s, they had very nice picture about the nucleon, because nucleon means you have bare nucleon and covered by or dressed by pions, pi 0 or pi plus, pi minus. And pi minus in this case for the neutron, because you have proton, bare proton, and pi minus will give you the neutron. and here bare neutron and pi plus will give the proton, etc. Then even they draw some charge distribution. So proton looks like this, and neutron looks like that. But what is interesting, if you take a look at the neutron, of course, neutron is a neutral particle. It doesn't have any charge. It doesn't carry any charge. Nevertheless, if you look into inside, then you have a positive charge, and at the tail part, you have a negative tail. So somehow pi minus is around here. However, this should be corrected because modern days charge distribution will be redefined. I'll explain very later. Okay, then of course in 1960, still Nucleon 3.0, so Gell-Mann wrote his seminal paper entitled Schematic Model of Baryons and Mesons, where the quark was for the first time suggested. At first, it was suggested as some mathematical artifact. He actually insisted that this is mathematical artifact because he was so much worried that the quark has a fractional charge, so it should not be measured experimentally. He was worried about it. But unfortunately for him, or fortunately, quark was found to be true particle in 1970s. But anyway, when he suggested that quark picture, the naive quark model naturally appeared. So here you have a SU3 flavor symmetry, but no dynamics, which means the proton consists of 2 U quarks and 1 down quark. If you take a look at nowadays some physics textbook in high school, then they nicely describe the proton consisting of 3 quarks. But this is all 1960s. The textbook should be rewritten. I insist. So this is somehow in the SU3 tensor, the baryon can be expressed in this way and proton explicitly written in terms of 3 states. Combining that, you can have a proton state. But keep in mind, there is no dynamics. This is a Nucleon 3.0. Now, in 1969, and now I call it Nucleon 4.0. Nucleon 4.0, Friedman and Campbell and Taylor, I think they are I think experimentally, sometimes braveness. You know, when that time they had a huge machine, so-called monster, the M machine. The M means monster. This is 2 miles long, the linear accelerator. You can reach very high energy. At that time, the most expensive accelerator in the SLAC. And then SLAC, the Stanford Accelerator Center, Stanford's Laboratory of Accelerator, something like that, the SLAC. SLAC was founded. Then, of course, they carried out some electron-proton elastic scattering first. Then they got some interesting results, including some resonances, but that's all. So many left for another physics, but they still keep going on with the electron-proton scattering. Then somehow they changed the detector with not the forward angle, but with the off-forward angle. Then they increased the energy of the electron. Then they received the surprising and really shocking data because this is elastic scattering, the total cross-section. But suddenly they got that kind of result. What does it mean? This means nucleon, the proton, may consist of some subparticles. The subparticles absorbs energy, some inelasticity. So to be inelasticity, you have to absorb some energies inside of the proton, inside the proton. So they got this result, and even they have some scaling behavior. That time nobody understood. However, in the similar period, the Feynman visited the SLAC and discussed this experimentally. Actually, he got his own idea. You know, I mean, he's one of the well-known physicists, in particular, as far as physical intuition is concerned, he is one of the best. Then he has some idea, because this is a hadron and proton, and this is electron. And now assuming that the proton is moving almost in the speed of light, then in that direction, the shape of the proton will be like a pancake because of this contraction, right? On the other hand, the inside, if subparticles exist inside of the proton, then inside let's assume that you have a clock, but this clock should go very slow because of relativity, which means in this the transverse plane, all the subparticles move very slowly. So when they are interacting with the electron, they have no time to interact with each other and also interact with this. So you can consider it as almost a free particle. This is before QCD, but even Feynman understood it in a different way. So then he called it partons. He never called it the quarks. But there is a reason. You see, the Feynman's office is very close to Gell-Mann's office. They both are professors in California Institute of Technology, Caltech. And actually, when Gell-Mann became a professor in Caltech, he was so happy because he has a chance to work together with Feynman because he admired Feynman. But unfortunately, Feynman is another guy who can work together with somebody. And also Feynman always teased the Gell-Mann because Feynman is a genius and Gell-Mann is even more genius because Gell-Mann is known to have five heads. We have only a single head, right? Single brain, but he has 5 brains. So pentacore. We have a single core, pentacore. So great genius. But usually when two geniuses meet each other, genius should be only one. They don't like each other. They wrote only 2 papers. Even this one paper was written together by external force, not by themselves. But anyway, Feynman definitely know the quark, but he disliked this name quark. So he called it partons. Then, of course, Gell-Mann got furious because he never called it quarks. Partons? What partons? Part plus ons? So ons from Greek, part from Latin. This is such an idiot name. So Gell-Mann always call it photons. Photons English word is kind of you cheat somebody, then you call it photons. So Gell-Mann call it photons, but Feynman call it partons. Nowadays we call it partons. So Feynman won. So then he also suggests the Bjorken scaling is correct because Bjorken first suggested, but Bjorken used very different theory like a current algebra. So experimentalists didn't understand what he was talking about. But when Feynman came up with this partons idea, now experimentalists started to understand what happens. So this is a result from the Kendall, Friedman, and Taylor. They got this result. It is almost independent of Q square, which means this structure function F1 and F2 can be considered as only single variable X. So this we call it the Bjorken scaling. And surprisingly, the valence force carry only momentum, the fractional, the 50% of the proton momentum. So the fraction of the momentum is just 50%. All other parts should be carried by C quarks and gluons. So nowadays, gluon carries almost 50% too. Okay, this is now somehow the results from HERA by H1 and JUICE collaboration. Then they got very interesting results. Of course, here you can satisfy some scaling, but when small x region and very large x region, the results are deviated. This is because of QCD. There is also the reason that the quarks decay into the quark antiquark pair because gluon energy is rather large in a small x. That's why this data rises. On the other hand, when x is large, then F2 falls off slowly because the quarks radiate gluons. All these diagrams are from QCD. So QCD doesn't have the strict Bjorken scaling, but more complicated dynamical reasons. Okay, here I'm very grateful to Samson. Samson drew this 4 diagrams. Thank you so much, because I had to hurriedly prepare this talk. So if you assume that you have a structureless proton, then this means this is Dirac particle. Then proton should carry all momentum, 1. Right? The x is simply, you can consider x as a fraction of the momentum. Okay? And if you, like Gell-Mann, if you assume that proton has a 3 static quark, then it should be 1/3, because each quark carries 1/3 of the proton momentum. But the real life is much more complicated, right? It should not look like this. So gluons should interact with each other. They exchange gluons with each other. Then you got this kind of result. But if you really measure experimentally, you have that kind of result. This means, as I told you, C quarks play an important role in small x region, as I've explained in the previous page. And that part is valence part. So here, gluons simply split into quark and antiquark, and also the quarks radiate gluons. All these things should be considered. Okay, then, and after QCD, so many models were suggested to describe the nucleon. Okay, lattice QCD is not a model. So you can try to solve QCD by using the computer. So there are also disadvantages of lattice QCD because it's expensive and defined only in Euclidean space. And also this nowadays are considered experiments, but it's really not the experiments. But still, lattice QCD gives us very important theoretical guidance. So lattice QCD is very important. But of course, when lattice QCD was first suggested by Wilson, then everybody believes that within 20 years, everything will be solved. But actually not. The lattice QCD itself has many problems too. Then quark potential models are often used, but this is also kind of mean field approaches because you have a potential which was made by all the quarks inside the nucleon. So the quark potential models of QCD summers and MIT back models. MIT back model emphasizes the confinement is important. And NJ models, their chiral symmetry contains breakdown is important. Actually, NJ model was appeared in 1962, one in 1962, before QCD. But after QCD, it turns out to be a fundamental theory, then NJ models was also rewritten in terms of quarks in 1976. Now, another wonderful model is a Scrum model. I'll explain this Scrum model it can be considered as one extreme case of this chiral effective theory for the nucleon. And now the Dyson-Schwinger approaches and the chiral Box-Soliton model. There are many models appeared. However, now we have to talk about the nucleon 5.0, modern view on the nucleon. This is new to you. So here, let me go very quickly because don't try to understand. This is actually somehow difficult part. But still, you have to know the QCD partition function. The QCD, in QCD, the fundamental degrees of freedom are quarks in QCD, not dynamical quarks. But this quark is different from the quark, Gell-Mann's quark. Gell-Mann's quark at rest quarks, of which the mass is 350 MeV or close to 400 MeV. On the other hand, here's the M hat is the current quark mass, the small, very small. Actually, that's the difficulty of the QCD. I'm not going to explain today, but here let me explain. This M hat is U quark mass, D quark mass, and strange quark mass. So U quark and D quark mass is 5 to 10 MeV. Now, we all know that the proton consists of 2 U quarks and 1 down quark. So let's add up the mass. So up quark mass is 5 MeV. So 2 5 MeV, so 10 MeV. So 1 down quark, let's say 10 MeV. So if you're adding up, you have a 20 MeV. However, nuclear mass is 940 MeV. Can you understand? 20 MeV of the quark mass will give you 940 MeV, the nuclear mass. It's impossible. Right? That's why the nuclear mass is very important. Can you imagine? Nucleon was born in 1920, as I explained. Now, 104 years passed, but we still don't know why the nuclear mass is almost 1 GeV. We don't know. So maybe more explicitly, 1.27 times 10 to the minus 27 kilogram. We don't know why. I'll explain. Because of that, now American government decided to spend huge amount just to understand why the nuclear mass is 938.27 MeV. So now, so you have that small quark, the mass current quark, and and also the gluons. So you have two important degrees of freedom, quarks and gluons. And then the action, QCD action can be written as here. So this is Lagrangian in Euclidean space. Of course, usually you can put your psi bar, will be enough, and minus m will be enough without m. Then we'll be in the Minkowski space. This slash is somehow covariant derivative, and G is gluon field strength, and A mu is gluon field. Then, of course, you can integrate over deep psi back up because this is a functional integration. Then you can have determinant. Okay? So this is, I mean, some of you probably learned it, but don't worry. So here we consider, instead of the gluon, we believe that instants are the most dominant ones, so we'll talk about the instants. Okay. So one important advantage of this approach is the chiral symmetry and its spontaneous breakdown are realized. You know that the most important physics in hadron physics is chiral symmetry and it's a spontaneous breakdown. Then, of course, you'd ask me very important question, or could be the nasty too. Where is the quark confinement? Of course, nobody knows quark confinement for now, mathematically. Also, the physically too. Of course, there are many tries and approaches to explain the quark confinement, but nobody succeeded so far. But no quark confinement, but quark confinement is important if you are interested in excited states, because quark should not be escaped. Quark should stay inside the hadrons, right? But as far as you are interested in low-lying hadron, the most important physics is chiral symmetry. Okay, this is instant another, but I have an idea. Whenever you attend some talk or some lectures, then suddenly some pages you find many formulas which you never heard about it, you never saw it in your life. Then there is one way to enjoy it. Just take a look at, like you watch some Van Gogh's painting. Okay? Just watch it. But if some of you wanted to understand real physical meaning, then you have to walk. Okay? So this means the instanton means self-dual solutions of Yang space in Euclidean space, because this is somehow classical. You can call it classical gluons. And of course, it depends on the gauge. So in a singular gauge, it is written in rather complicated form. Let me explain one by one. Here you have important thing is that this is the tooth-thumb symbol. You don't need to know in detail, but the Z is somehow position of the instanton, and rho is the size of the instant. We call them as some collective coordinates that are zero units. And on top of it, when you have to rotate in color space, because we have a SU3 color group, because this is gauge group, then you have to rotate inside the color space. So you have to introduce also color orientation. So collective coordinates are altogether 4 NC. NC is the number of colors. So in the real nature, NC should be equal to 3, but we can assume that NC is going to infinity. And instanton means, physical meaning is that it explains simply tunneling. So even in quantum mechanics, you have instantons. But probably in graduate school, have you ever solved this double ray potential? There are two different ways of double ray potential. One way is just to solve directly Schrödinger equation. Then you would have as a solution some cylindrical function, something like that. I think I never saw such functions in the textbook, but you can get the answer from the mathematical. So nowadays you have a mathematical, so it's easy. Or you simply go to the Euclidean space, which means you simply over this potential. Then it becomes kind of classical physics. You have one ball on the one hill, then ball fall down and it goes up and stay here. This is kind of tunneling. The tunneling is just classical trajectory. That classical trajectory, we call it the instanton. So instanton means some simply tunneling. So here in QCD, simply each state in the vacuum is classified by Chern-Simons number. Chern-Simons number is also related to gauge group. And then this instanton means tunneling between different vacuum states. But all this vacuum is numbered by integer number. So here, +1. This we call it Chern-Simons number. That we call it instantons. Okay, already 50 minutes I spent. So let me skip it. So instanton is important. Okay. Let me skip it because I don't want to bother you, all these things. Hey, okay. This is one kind of schematic diagram. Okay. So this is instanton and anti-instanton, instanton and anti-instanton. Somehow they interact with rather repulsive way. So the system is stabilized. So instanton has a right-handed chirality and anti-instanton has a left-handed chirality. So now quark interacts with this. Quark hops from instanton to anti-instanton, instanton, anti-instanton, instanton, anti-instanton. Then this chirality is changing from left to right, right to left. What does it mean? If you have a massless particle, chirality is always determined, left-handed or right-handed. For example, neutrino has a right-handed. Antineutrino is left-handed, right? It is well defined. But same, if the quark is massless, it has the chirality or helicity. Helicity is a good quantum number in this case, because helicity can be identified as a chirality when in the massless case. But now this chirality is changing. What does it mean? Quark starts to acquire the mass, okay, by interacting with instanton and anti-instanton. Then it turns out that you have a dynamic at quark mass, the M of P. This is also momentum dependent. What is interesting is that this is the result from the instanton vacuum, while this is lattice data. Of course, you have to keep in mind that lattice calculation, they use different gauge than here. Here we use singular gauge. The nevertheless is really comparable. So then the mass is around 3.35 MeV, so 350 MeV. So 350 MeV is very different from 5 MeV. So this mass is generated by spontaneous breakdown of chiral symmetry. So physically saying, this dynamic quark was stressed by gluons. The gluons enter the play. The gluon is very important. You should not ignore the gluons. This is a lesson from today's lecture. So anyway, all the detailed things, let me skip it. Important thing is that quark got mass. So do you know, this U quark mass is 5 MeV and D quark mass is 10 MeV. Do you know how these quarks get mass? Because of the Higgs part. Higgs will give you the answer to the U quark mass and D quark mass, but 5 MeV and 10 MeV. But this chiral symmetry and its spontaneous breakdown will give you 350 MeV. So visible universe, the mass of the visible universe was given by this dynamic quark mass. Yeah. So let me ask you, I'm very much interested in also dark matter, all this high energy physics stuff, but I'm more interested in visible universe because I can see it. Because invisible, I don't see it. So I have only interest. Now for the visible universe, which one is more important? Higgs mechanism or chiral symmetry and spontaneous breakdown? Definitely chiral symmetry and spontaneous breakdown. Okay. Of course, I'm not ignoring the Higgs mechanism, but don't ignore also all this important physics. Okay? This I want to emphasize it. Okay, so what is the merit of the instanton? Now in the lambda QCD, if the QCD is renormalized and after dimensional transmutation, you would have lambda QCD, which is known to be 280 MeV. MS bar is the kind of renormalization scheme, minimal subtraction scheme. Pi is some modified minimal subtraction scheme done by, who is that? The Badin and not William Badin, not the superconductor Badin. William Badin and also all other his collaborators suggested this MS bar scheme. Then there are two important parameters. Rho bar is average size of the instanton, and R bar is the interdistance between instantons. But of course, they are not free parameters. They are all fixed by this value, 280 MeV, through some formulas. And we obtain also M0. This is not free parameter. Then 350 MeV is obtained by set point approximation. Then also, then naturally you can have a quark condensate. Quark condensate is, you can call it the order parameter in the statistical physics. So broken phase and unbroken phase. So unbroken phase means chirosymmetry is still there. The broken phase is chirosymmetry is spontaneously broken down. You know that in statistical physics, whenever phase transition appears, right, you have some finite order parameter. Chirosymmetry and its spontaneous breakdown is exactly the same as the phase transition in statistical physics. Then all low energy theorems are satisfied, and even U1 axial anomaly is well explained. On top of it, you have a 2NF. NF means flavor number. So if you have a U-quark and D-quark, you have a quark-quark interaction like NJ-like interaction. But SU3 case, you have a 6-quark interactions. So all the things we obtain. Yeah, this looks very beautiful, isn't it? So let's skip it, yes. Okay, so here we apply this method to light quark systems and single heavy baryons and quarkonia and heavy light quark systems. Now heavy model. I'm now preparing a paper about it, and also it's a very nice result. So, however, in this talk, let me consider the light quark system, in particular only low-lying baryons, okay? The nucleon. Again, this is, I don't want to bother you. This is starting point. Here, let me explain, in particular, it's related to scum model, okay? Now I have the trace law. This is after integrating over the quark field, you have a minus NC trace law, and U gamma 5 is pseudo-Goldstone boson field, or you can call it chiral field, which consists of pions and kaons and eta. But here we have only pions, because kaon and eta are treated in a different way. Then in the case of a small momentum, the small pion momentum means this is pion momentum. D slash is pion momentum. ID slash is pion momentum. So you simply carry out the derivative expansion. Derivative expansion means that you use as an expansion parameter the pion momentum divided by dynamical quark 350 MeV. So which means pion momentum should be indeed small. Then I did it actually in 2004. I carried out this derivative expansion, and we obtained very nice, wonderful result, I would say, in comparison with the chiral perturbation theory. So then this is complex function. So you have a real part and imaginary. The real part, you have L2, L4. So L2 is well-known Weinberg term, the kinetic term, with the pion decay constant. Pion decay constant is also well reproduced, 9030 MeV, 93 MeV. So L4 is so-called Gassa-Leuchtfiller term. L4 is also, if you take a large NC limit, these three terms is reduced to one term. This term is called the scum term, scum Lagrangian. Okay. So in the scum model, you have a L2 and L4. So L2, but if you include only L2, then soliton becomes unstable or unstable. So you have to introduce the scum term or Gassa-Leuchtfiller term to stabilize the soliton. Then you have the scumion. So this scumion is one limit of this model, because scumion considers only two Lagrangian, and on top of it, in the SU3 scumion, you need this term, Bethe-Jumino-Witten term, because Bethe-Jumino-Witten term constrains so-called right hypercharge in the quantization. So to have the properly baryon number equal to 1, you need Bethe-Jumino-Witten term in the scum model. So this Bethe-Jumino-Witten term is also related to the topology. Even in gauge theory, you can have similar situation. In gauge theory, we call it the Chern-Simon term. Okay? Here, in the usual case, the Bethe-Jumino-Witten term, which is related to also axial anomalies. So you can have that result. Okay. Now, we are following again Witten's seminal idea. Witten considers baryon in the large NC limit. Simply he considers baryon consisting of NC quarks. not 3 quarks, but NC going to infinity, the infinity number of quarks. Then this infinity number of quarks make the vacuum polarized. Then this vacuum also changes NC quarks because they are interacting each other in a self-consistent. This self-consistency you can find in many different places in physics. For example, in nuclear physics, and also in many body problems, in condensed matter physics, and even in optics. So here we use the number of color as an implicit expansion parameter. Then baryon can be viewed as a state of NC quarks bound by measured mean fields. And this here, the conclusion is the mass is proportional to NC, while the width is of order, just the order 1. This means mesons are weakly interacting. And also the quantum fluctuations are suppressed by 1 over NC, so you can ignore it. So we don't consider quantum fluctuations of the mesons. So what is the mean field in quantum field theory? You have an action, so you have some system you are interested in, and you always have to define some actions or Lagrangian, right? So you write down the Lagrangian and solve the classical equation of motion. Then you found the solution. That solution, we call it the mean field. This is mathematically well defined. This mean field was so successful. For example, there are many particles, but this particle makes some collective interaction. This collective interaction, let us call it the potentials. So this is a mean field potential. Then assume that one particle is bound by this mean field potential. This is the mean field approach in physics. So nuclear shell models is a kind of mean field, and Ginzburg-Landau theory for superconductivity is also mean field approach, and quark potential models are also kind of mean field. I think you can also interrupt any questions. Okay, this is not important. Okay, let me skip it. Okay, so picture of this model is as follows. At the very beginning, there is nothing. There is only vacuum. But this vacuum is QCD vacuum. QCD vacuum is so complicated because of interactions. So they are interacting each other very strongly. You cannot deal with this vacuum structure mathematically. You need a certain approximation. So nobody proved this is kind of scenario or some picture. Then you have a mass gap. This chiral symmetry is broken down. But if you really can prove this mass gap exists in the QCD vacuum, then you would receive a Nobel Prize. And at the same time, you would receive $1 million from this Clay Institute. This is a well-known problem. Right? Also, this is related to the quark confinement. But of course, you have to prove mathematically, not physically. This is a mathematical problem. Okay, now let's put 3 quarks. But here 3 quarks, but this is NC quarks. Okay? If you put NC quarks, as written suggested, then they are interacting each other. Quarks are interacting each other. And also vacuums are interacting each other. The vacuum is polarized because of the presence of these NC quarks. And they are interacting each other self-consistently. So because of that, these vacuums are polarized, vacuum has changed it, and also the NC valence quarks are bounded by this, bound by the mean field. So valence level, energy decreases. So C level, energy increases. So this is stabilized because energy is increased, it is stabilized. Okay. Okay, this is some technical thing. Let me skip technical stuff. I will give the copy of the PDF file to Professor Matt. And if you're interested, just get this file and read it. May I skip? Yes, I think you would like it. Yeah? If you really want to understand, I will explain. I can make you sleep. Okay, another complicated stuff. Skip. Okay, this is important. Now, this mean field approximation is nothing but a Hartree approximation. You all know that already. What is a Hartree approximation? You don't know the shape of the potential. Give any potential in the Schrödinger equation. But here, of course, we solve Dirac equation. So assume that you are interested in solving Schrödinger equation. and put some test profile function, or you can call it potential, then solve the Schrödinger equation, or Dirac equation, then energy of quarks and eigenvalue and eigenstate, you obtain it. Then using eigenvalue and eigenenergy, you minimize classical energy. Then you can derive the shape of the potential. Then put this new potential into here, do it again until this classical energy is minimized and stabilized. Actually, this is the most time-consuming part of my research. When I was a postdoc, it took 2 hours to derive one potential. No, sometimes 1 day. But now my students need only 30 minutes. Still they are complaining. 30 minutes are too long. But when I complained, when I was a PhD student, whenever one fit took 2 hours, I complained it to my supervisor. My supervisor said, when I was a kid, which means when I was in your age, but be very careful. When senior people tell you, when I was in your age, then I usually don't listen. Right? Because he simply doesn't understand me. So he told me, that time you have to make a punch. You make some punch card to run the code. So he has to keep this code. Then he has to walk maybe 10 minutes to 15 minutes to computing center. Then give this to the operator. Then he has to wait for 3 days to get the result. But this code, the same code, now it takes only 1 second. Amazing, right? Anyway, now you can solve it by using 30 minutes will be enough to get the final profile function. Okay, this is quantization. But here I told you that we ignore quantum fluctuations. However, you're not allowed to ignore the zero mode quantization. Zero mode means you can change the state without causing energy consumption. So you have to really deal with completely. So we simply carry out the zero mode quantization. To do that, we have to introduce collective coordinates. So this collective coordinates here, rotational matrix. So A is here R. This. It is actually typos. It should be A here. Because SU3, we usually put A. And also translational zero mode. Because we are interested in calculating form factors, this translational zero mode is essential. Because Fourier transform naturally appears from this translational zero mode. And then you obtain some collective Lagrangians. Then you nicely describe the mass spectrum of the baryons. Here, now Y prime is called the right hypercharge, which should be constrained. This is constrained by the NC balance quarks in this approach. But in the SCOM model, this is constrained by Vest-Juminoto. So this is different picture. Okay, so after constructing this model, the model was applied to many mass splittings, all different types of baryon form factors, and pattern distributions and quasi-pattern distributions, GPDs, single heavy baryons, and now we are even working on the excited baryons. Okay, here let me give one example. Maybe Perry will be also interested. This is electric charge. Let me show you here. This is the neutron charge. Okay? But be very careful. The charge density is not Lorentz invariant term. The form factor is Lorentz invariant. You see, this is proton form factors. We computed all this lambda C plus the singly heavy baryons, and we compared this result with the lattice data, a very in good agreement. You see, this is a big gap, which means if you have a heavier hadrons, this is more compact than the proton. But this idea can be applied to also the form factors in the reaction calculation. Okay? The idea came from actually this calculation. This is more compact. Okay, now Nucleon 5.0 in the EIC era. The EIC means electron-ion collider. So this is actually very important. Let me spend some time because you will be interested. Okay? if you take a look at any textbook about particle or nuclear physics, or even condensed matter physics, they define the form factor in that way. You have a charge distribution or some distributions. Usually, if you carry out the Fourier transform, you would have form factors. Then, of course, this distribution or this density consists of the wave functions, but this wave function can be obtained by solving the Schrödinger equation. Keep in mind, h bar is equal to 1 in our case. Then, so if you take a look at hydrogen atom, size of the hydrogen atom is 0.53 angstrom. This is Bohr radius. But Compton wavelength is 2.10 to minus 6 angstrom, because the Compton wavelength is the inverse of the mass. Okay? The inverse of the mass of the hydrogen is 2 times 10 to the minus 6 angstrom. So ratio is 10 to the minus 6. This is so small, so relativistic effect is not at all important. Then what about the nucleus? Nucleus is similar. Size of the nucleus around 5 Fermi. Maybe if you have a lead nucleus is 208. The number of the nucleon is 208. So then the size is 5 Fermi. Then Compton wavelength is 0.001 Fermi. So if you consider ratio is 0.002. The non-relativistic treatment is absolutely valid. However, what about the nucleon form factors? Even in the textbook, it is written that the nucleon form factor can be treated in this way, in the similar way. However, this is not correct, because the probability interpretation is wrong in a relativistic case, because you cannot find, for example, initial state and final state are different when you measure the charge distribution of the nucleon or proton. Okay? And also this ratio is 0.25. It's close to 1. So you should be very careful. So here is an idea. So if you take here I already discussed, so please take a look at here. So if the momentum of the probe, or electron or photon, whatever, if it is larger than the nucleon mass, then initial and final momentum are different. This is recoil effect. So nucleon cannot be treated non-relativistically. On top of that, particles will be created and annihilated. This is also important. So nucleon or proton is totally relativistic object. Some people argue that, well, we consider the proton in the potential model non-relativistically. The results are very nice, but results are not everything in physics, right? Because you have 3 parameters. You can fit an elephant. We all know that, right? So results are not everything. And let me skip it here, but still 3-dimensional charge distribution is a physical meaning. This is quasi-probabilistic meaning through the Wigner distribution. Let me skip it. Only this idea is important. Okay, this is the situation, the present situation of hadron structure, or more I would say maybe the structure of the proton. So this Wigner distribution as a function of x is Bjorken x or momentum fraction. Bt is impact parameter. Kt is the perpendicular momentum, transverse momentum. So this is 5-dimensional quantity, which is quite complicated. So what usually people did is simply either integrate over this impact parameter space or transverse momentum. Then you would have a transverse momentum distributed. TM, this is now a big issue, or impact parameter distributions. Or if you make a Fourier transform, you would have generalized pattern distributions. People are interested, and this is really a hot issue in hadron physics. This is 3-dimensional physics, because you have a 3-dimensional. Bt is impact parameter in transverse plane, the 2-dimensional, and x is a longitudinal component, the 3-dimensional. But you further integrate over some variables, you would finally have 1-dimensional. So well known is that the fx can be obtained by integrating over transverse momentum and also the Bt, impact parameters. Then you would have a pattern density, or you can have form factors. In particular, this is form factors, but now I explained the form factor is a Fourier transform of some densities. This is old concept of the nucleon. Okay? That's why I'm arguing that the textbook in high school should be rewritten, and also textbook in universities should be also be rewritten. So it should be modernized. Okay, this is a picture. So now pattern distribution contains everything. Okay. This is transverse plane. So usually form factor gives information about the transverse plane, BT. Now nucleon is moving that direction, x direction. X is momentum fraction here. And this is the pattern distributions in longitudinal components. If you compare, if you combine longitudinal and transverse components, you would have GPDs, generalized pattern distributions, and you can discuss about the nucleon tomography. Okay, now this is the concept. On old days, we simply consider that simple Feynman diagram to study the structure of the nucleon. But in the case of the tensor form factors or gravitational form factors, we cannot find the proper probe. So there is no particle with sigma mu nu structure. And G mu nu is the graviton, but graviton is so weak, you cannot use directly. So to avoid it, we can simply understand the form factors as millimoments of the GPDs. Then you can study, for example, electromagnetic form factors is just the first moment of the vector GPD. The second moment of the isoscalar GPD is called gravitational form factors. Now let me discuss how many times, because nobody asked a question then. 11 minutes, okay. So here, let me only emphasize important things. This is important. Okay. Now, how can you deal with this physical observables? QCD is so difficult to solve it, so you can rely only on the lattice QCD. The QCD operators you can define. However, there is a way to deal with these gluonic operators in an effective manner. So you can define low energy effective quark-gluon dynamics, emphasizing the this symmetry breakdown of chiral symmetry. So scale is around 1 GeV. Then we can define effective QCD operators. For example, here gluon operators, and twist 2 is leading order. The twist is also kind of a quantity, which means dimension minus spin. So when you define the importance of the operators on the light one, they use the twist. So twist 2 is the leading order. Now, today's third subject is the energy momentum tensor and gravitational form factors. So you have to start from the energy momentum tensor operators. So QCD operators is well defined. Of course, by the instantons, gluons can be integrated out, but you also have to consider gluons explicit. In that case, we simply replace gluons by instantons and try to derive some effective operators. Okay, that's what we did. But we realized that when I carry out the flavor decomposition of the gravitational form factors, and we have to be extremely careful about this twist 2 and twist 4 operators. Now, from now on, I'll talk about more technical things. But this is electron-ion collider at the Brookhaven National Lab. So I think the collider will start to run in 2030s, maybe 2031 or 2034. So within 10 years, so we are going to have a new accelerator. So they are really now under construction. Here the specifications of this EIC is given here. I took this part from CDR report, the CDR of this EIC. So center of mass energy ranges from 20 GeV to 100 GeV. Maybe later can be upgraded to 140 GeV. Then you have ion beams from deuterons and heaviest stable nuclei and high luminosity. This is also important. And highly spin polarized electron and proton and light ion beams. This highly polarized beam is very important to study proton spin. Let me ask you a question. Do you know the spin of the proton? You know the spin of the electron. So physically, also theoretically, we know that this naturally arises from special relativity. Electron should have spin 1/2. But then what about the proton? Proton is a fermion. Fermion must have spin 1/2. Right? 3/2, there is also particle with spin 3/2 and 5/2 and 7/2. The fundamental proton should have spin 1/2. Then question arises. Why does the proton have spin 1/2? You would say, okay, it consists of 3 quarks. Quarks is also fermions. So spin 1/2 times spin 1/2 times 1/2, you can have a spin 1/2, quantum mechanical. But I told you, inside the proton, you have gluons, you have a quarks and antiquarks pair, and you have valence quarks. They should all contribute to the nucleon spin. In 1987, muon collaboration, the European muon collaboration, so the EMC experiment, carried out a very important experiment at CERN. They found that the contribution of the valence quarks to the nucleon is around 30%. Can you imagine? Where does it come from? The 70% rest. Where does the rest of this spin come from? This is the important issue for EIC. So they have a very clear-cut mission. First mission, how does the mass of the nucleon arise? And how does the spin of the nucleon arise? Then what are the emergent properties of dense systems of gluons? So now US government or Department of Energy decided to spend huge amount of money to understand the nucleon mass, the spin of the nucleon. So this is everything for the visible universe. So you must have interest in this visible universe. This is the fundamental question. That's why now they decided to spend a huge amount of money. So if some of the young generation, actually this accelerator is not for me because I'm going to retire in 2029 before the EIC starts around. So this is not my accelerator. It's Samsung's accelerator. So I think this is really for the young generation. So in the one word, this is physics of gluons. Now you have to have an interest, or you have to work on the gluons. Now you cannot ignore. You can ignore no more the gluons, and also once you consider gluons, things are getting more and more complicated. Okay, now this is gravitational form factors. Let me skip it. Because you will have to. So you see, I'll tell you. Gravitational form factors contains the mass of the nucleon and the spin of the nucleon. So in order to understand the mass of the nucleon, mass and spin of the nucleon, you have to understand gravitational form factors. That's why the gravitational form factor is so important nowadays. Okay, all technical issues, let me skip it. So again here, role of the gluons are important. Okay. So this is 3D distributions. I criticize it. Let me skip it because all technicalities. Let me see some interesting things. This is interesting. This is related to the stability of the proton. Even nature accepted this experimental, not really experimental data, but empirical data. The book, Volker in Jefferson Lab, they used experimental data and extracted some empirical results for the pressure density of the proton. So if you integrate over this density, it should be equal to 0. Because the proton is existing part, right? So proton should be stable. Then this is our calculation, and this you see, what is interesting is the red curve is from the chiral quark-solitary model. They put, we didn't put, they put. So only the chiral quark-solitary model nicely describes the proton, the pressure density. So already model is so successful. Well, of course, only difference is they use 350 MeV and we use 420 MeV. That's why this is some size is different. Because in SU3, we prefer to use 420 MeV because we consider only nucleon, lambda, sigma, and cascade. So since we consider all high currents, so we use 420 MeV. So now experimentalists started to consider this pressure densities. This pressure densities is related to the D terms, which I skipped, and this is another. But of course, what is important thing is that they assumed the flavor blindness, but this, if you really want to apply flavor blindness, you have to work in SU3, not in SU2, because we explicitly show that only in SU3, the flavor blindness can be applied. Okay? But which means you cannot ignore the strange parts inside the probe. This is the message you have to take home. Okay, this D term is very important, this D term. And strange quarks is very important only for the D term. Strange quarks are not important in the mass and in the spin, but for the D term is very important. D term is a new quantity. D comes from the German word, which means pressure. So this is related to the pressure, very important. And we obtained also mechanical size. And we have several different types of size, mechanical size and mechanical radius, charge radius. Then we finally obtained mass radius, mechanical radius, and charge radius. Charge radius is the largest, and mechanical radius is the next one. And this is mass radius. Now we work on this mechanical engineering in the proton. Okay? So engineers will like it. Okay, let me skip it. Okay, this now we can also study force field inside. So down quark, strange quark, and up quark. But of course, if you add up, then this should be equal to 0, because system should be stabilized. Then what is interesting is that the up quark contribution is balanced down and strange quark contribution. I computed by using the unit of the Newton, because you are familiar with the Newton. Newton is the unit of the force, right? Inside the proton, you have a 50 kilonewton and 50 kilonewton. So how many trucks in your body? Amazing, right? In such a small particles, the force is amazing size. That's why we exist now. Since proton is stable, with such a force balance. Okay, the lesson is keep it. Okay, thank you very much.
Thank you very much for very nice presentation and containing so many information inside. Yeah. Now, I realize that mechanical engineers should be interested in this. We invite now, starting inviting mechanical engineer to engineer the proton. Okay, I open time for question now. Yeah, whatever question you can ask or you can raise. Okay, let me start the question. I know that you are confused a lot with this presentation. We know that the spin crisis or this EMC effects, that the contribution of the quarks to the spin is only 30% for proton, in the case of proton. People calculated also the contribution from C quarks and from gluons, etc. Yeah. How much the contribution if you also include gluons and C quarks?
This is very important question and also very difficult questions, because for example, Okay, here I simply decompose the iso triplet J, but you can ignore it. So here, this is quark part. Gluon part I didn't consider here. So quark, the valence quarks should contribute to the spin of the nucleon and also orbital angular momentum of the quark should contribute to the also spin of the nucleon. Up to here is clear, but concerning the gluons, it is extremely difficult to decompose gluon spin contribution and gluon the orbital angular momentum contribution. This is gauge dependent or skin dependent. So it's very difficult. So still under discussion, but we know one thing we really know is that quark contribution is smallest.
Yeah.
So 30 now is 36%. 36%.
But including this angular momentum.
No, angular momentum is different.
Different.
So I believe that the quark orbital angular momentum is the most important.
Most important.
Some people say that gluon is also important. Actually, that is the reason why EIC started.
Yeah.
Because the previous experiment from the RIC, the spin physics, RIC experiment, they said gluon's contribution to the nucleon spin may be large.
Yeah.
But here point is maybe.
Maybe. Yeah. Must be proven
but
by
from this instanton point of view, their contribution should be small.
I see. Yeah. Okay.
But of course, we could be wrong.
Yeah. That's why U.S. government decided to spend so much money,
huge amount
for this
$1 billion. Yes.
Yeah, this what is this lab Brookhaven?
Brookhaven, the EIC.
EIC. Yeah, this EIC, and the effects also hits the Jefferson Lab. You know, Jefferson Lab now has difficulty to have grants because the DOE cut the budget. The budget is shifted to this EIC, I think. Yeah, if I'm not mistaken.
Yes, yes.
Probably. Yeah.
I think the Jefferson Lab, they try to upgrade the electron machine, but as far as I know, maybe because from DOE's point of view, within 10 or 20 years, the Jefferson Lab will be probably absorbed into EIC because the DOE decided to keep only 2 accelerators. I heard from someone in DOE, 2 accelerators for nuclear physics. One is EIC, the other one is FRIP at Michigan. It's low energy physics.
Oh, okay. Then Jefferson Lab will be shut down.
But anyway, they decided to work together with EIC. So somehow.
Okay. Yeah. Okay. More questions. Please, if you have a question.
Maybe students.
Student question. Yeah. Let's read one.
Check. Hello, Prof. Kim. My name is Muhammad Ridwan. We've met before several days.
Yeah.
Okay, so I would like to ask a question. I mentioned that you're working on the instanton vacuum to investigate heavy mesons. Am I right?
Yeah.
Okay, so the question is, what are the special feature of using instanton vacuum if we works on the heavy mesons? Because my thesis works on the heavy quarkonia by using the light from quark model, because I'm very interested if we investigate the other methods such as instanton vacuum.
Yeah, thank you very much. Actually, for each subject is a good seminar project. So we worked on the quarkonia. Also, we constructed instanton effects on the heavy quark potential. You know, heavy quark potential usually consists of the confining potential, of course, totally phenomenological potential with string tension. And second one, they said it is derived from perturbative QCD from one-gluon exchange, the Coulomb-like interaction. Then, of course, they have only 2 terms. This is a well-known Cornell potential. But these parameters are free parameters. For example, in the one-gluon exchange, they have a alpha S, strong coupling constant. But if they really take the value from perturbative QCD, you are not able to describe all spectra. This is impossible. That's why they have to use as a free parameter. On top of that, since you introduced also mass terms, so you have the Champok mass. Champok mass in the potential approach is taken to be 1.8 GeV, but physically it is 1.2 GeV. But to fit the data, they used 1.8 GeV, right? So these parameters are, they are well-defined parameters physically, but they use somehow large values. Now we consider the instanton, but we realize that instanton contribution is rather small. For example, to the heavy quark mass, only 70 MeV. This is interesting. Even though instanton effect is so small, by introducing this instanton potential into the heavy quark potential, we are able to reduce these free parameters, getting closer to the physical values, which indicates that instantons are still coming to play for the heavy quark system. Now then, what about the heavy light quark system, like heavy mesons? Heavy mesons consists of one heavy quark and one light quark, conventional one. Of course, you can consider also tetra. Nowadays, tetra quark is big business. So 2 heavy quarks and 2 light quarks, right? But here, let me consider only conventional ones. But whenever you have a light quarks, you cannot avoid the instantons. Instantons are automatically involved whenever you talk about the light quarks. That's why we actually recently derived the effective action for heavy light quark systems. So now I'm writing a paper. And previously also, Musakhanov in Uzbekistan, he also constructed this instanton-induced interactions. But here, my students and my postdoc, who was a former student of the Musakhanov, we succeeded in constructing the effective action. So we computed the decay constant of the D meson and A B meson. They turn out to be very nice. And also we computed also heavy quark mass. But of course, this is not the end of story. But here we only considered the light flavor number equal to 1. This is too simple. So we have to introduce NF, the flavor number equal to 2. This is under now study. So whenever there is a light degrees of freedom, you cannot avoid instant. This is the conclusion. No free parameter. I told you, one great advantage of this is no free parameter. No single free parameter.
No free parameters. Yeah. Okay. More questions? Yeah.
Okay, thanks for the opportunity. This topic is very interesting. My name Bayu. I'm from basic graduate program. My question is about in history of Nucleon 2.0.
Yeah.
Basic the experiment is proton have magnetic moment.
Yeah.
My question is where the magnetic moment come from?
Yeah, I can show you. So your question is the magnetic moment.
Where does this magnetic moment come from? Where? This
magnetic moment. Yes, I can explain. Yes, I understood. So your question is the origin of this magnetic dipole moment, right? So again, that's very important question because let's consider, for example, neutron. Proton is clear because it's positive charge. But neutron is charged, is a neutral particle. Even though it is a neutral particle, magnetic moment is minus 1.91, which is very large, right? But this comes from the, you know that quarks is rotating inside the proton, right? So it has some kind of current J. So magnetic moment is defined in electrodynamics, 1/2 R times J, right? R is relative momentum, right? J is somehow the current. So it's also related to the angular momentum too. So somehow we computed this operator, I cross J, okay? So J should be defined. J is vector current, like a vector potential in the electromagnetic, electrodynamics. So somehow the origin of this magnetic moments is 2.9, 2.79 comes from the quarks charge and also current. And also, I don't know, gluons doesn't have any charge. So maybe this interaction between gluons and quarks will be important, but gluon itself, I think, will not contribute to the magnetic moment because it doesn't carry any electric charge, right? But to have the magnetic moment, you need some charge. The charge is the source. This may be my answer. Yeah.
Yeah. Okay. Any other question? Yeah, Pak Aziz, please.
Yes, my name is Aziz Majidi. As I'm a condensed matter physicist, so I'm kind of an outsider of this field.
Yeah.
So I'm not gonna.
Yeah.
Problem in condensed matter system, for instance, if we have an ion having some electrons, since this ion has the structure uh, built in by the electrons, right? And the electrons have the excitation, they are dynamic. So the ion can at some time have certain spin,
Yeah.
total spin because of the internal spins, right?
Yeah.
And this can change.
Yeah.
So what about
Yeah. Yeah.
I only wonder, as you showed that you include gravitational form factor.
Yeah.
To me, I simply thought that everything that you take into account in your theory must have a reason of, let's say, the energy scale, right? Since gravity is so weak compared to the other interactions, especially in very small scale, right? Microscopic scale. So why would you still need to include gravitational form factor or gravity in this calculation anyway? So those are just two questions.
Thank you very much. So let me answer one by one. The first question is about probably the skyrmion, right? Am I right? It's related to the skyrmion in condensed matter physics.
No, the first question is whether you can.
Spin of the proton in which? Well, here is a different because we consider the isolated nucleon consisting of the subparticles, including quarks and valence quarks, C quarks, and gluons. The gluons are integrated out, and gluon is realized as a pion mean field in this case through the instant. So the spin of the nucleon is anyway 1/2 because we are interested in the isolated nucleon in free space. Even though you put the nucleon inside the nuclear matter, spin of the nucleon 1/2 will never be changed because it is spin 1/2 just belongs to the nucleon. Right? So this is the idea. And the second question is about the gravitational form factors. That's a very good question. I think because of that reason, some people dislike the word gravitational form factors. Then why we are using this word gravitational form factors? The first reason is it sounds fancy. Second reason is that this is also related to somehow gravity. Because here, as I told you, you have a G mu nu. This is graviton. Of course, G mu nu never interacts with nucleon. Of course, it interacts because nucleon has a mass. Any massive thing will be under the influence of the gravity. But the mass is so small, you can ignore it. And so even in nature, it is difficult to find the graviton interaction. Right? So one way to consider, is this millimoments of the GPDs. GPDs is non-perturbative part of the deeply virtual Compton scattering. So in that case, you can consider two photon exchange. Okay? Two photon exchange means this two photon has some tensor structure. Right? So this tensor structure mimics also gravitons. This is one reason. And second reason comes from the theory. I will explain you. Yeah, here. So why gravitational form factors? Because to do that, you have to find energy momentum tensor. What is energy momentum tensor? You have a Hilbert-Einstein action given in this way. So you have this is Ricci scalar, R is Ricci scalar. The second term is related to the gravity and also what is the curved space. Here you are in the curved space, and second term is matter part in general relativity. This matter part, you have LM. So this is Lagrangian. So you can put some Lagrangian with fermions. Our Lagrangian you can put here. Then you simply consider some weak gravitation. So you can simply somehow curved space is rather almost flat. So this eta mu nu is flat the metric. Then G mu nu is for the curved space. So you simply expand in the vicinity of this flat space. Then you can carry out this functional derivative of the SM here, the Hilbert-Einstein action with respect to G mu nu, the metric. Then you can obtain the T mu nu. T mu nu is energy momentum tensor, the matter part. So you know that Einstein equation is G mu nu is equal to T mu nu, right? So we are dealing with this T mu nu. That's why we put the name gravitational form factors. But some of them really dislike these gravitational form factors because this is misleading, as you said. That's why they call energy momentum tensor form factors. So in my case, I don't mind. So I sometimes use gravitational form factors. I submit a paper to PLD and referee dislike, no, don't call it gravitational form factor. Okay, I'm using energy momentum tensor form factors. And also there is even more serious problem. Here, you see the CEVA form factors. If you add up all the flavor, this should vanish because of the conservation of this energy momentum tensor. So can you read here, cosmological constant? So some people started to call the CEVA A as a nuclear cosmological constant. I was really somehow impressed. Oh, that sounds nice. I started to use it. Then again, the referee said, no, this you should not call it cosmological constant. It has nothing to do with cosmology. Okay, I agree with you. I changed it. I just CEVA form factors. But you see, I don't like the CEVA because in Korean, CEVA is kind of insult, a bad word. So I would rather call it cosmological. So I would like a cosmological constant. Actually, because of that, I really dislike tetracopter, CEVA C, CEVA C. So CEVA is somehow very bad word in Korean. That's the reason.
Yeah, actually, I would like to add that we could change the proton spin, but when this proton is excited to the nucleon resonance level. Yeah.
Okay,
Nuclear-
that's another one. Yes, yes.
Nucleon resonance could have spin until 15 half.
Yeah, yeah, yeah.
15 divided by 2. This is very large.
Yeah, yes. Actually, but still here different language.
Yeah.
For example, condensed matter physics or in quantum mechanics, you call it excited states.
Yeah.
But
Yeah.
we call it, because of relativity, we call it excited particles.
Particle. Yeah. We call it excited particles. So
Also collective mode in condensed matter physics, we call it quasi particles. Yes.
I would like to ask you. This is always off automatically. We know NC is equal to 3.
Yeah.
Why you could consider? Oh yeah, online. Okay, okay. I skip my question
Okay.
because there is online questions. Okay. Okay, from Gil. Battery is out. Which one? How can QCD vacuum structure be visualized? There is the first question, I think. Yeah.
What was the question?
How can QCD vacuum structure be visualized? Can you visualize?
Visualize.
Yeah. But there are so many questions. Yeah. Maybe you can answer them one by one.
Okay, I'll do. That's
Could you?
that's not my job.
Yeah.
So I mean, I'm a theorist. Let's people use sometimes visualize the QCD vacuum. Of course, you cannot see QCD vacuum. And also this visualization is dangerous from theoretical point of view, because it is many times it is misleading, right? So because simply you cannot see QCD vacuum. Yeah, yeah. Visualize the emptiness. But vacuum is so complicated. Vacuum, you know, who first defined vacuum? Do you know that? Democritus. Yeah. Democritus defined the atom and vacuum. Of course, the meaning of vacuum defined by Democritus is different. From his point of view, vacuum is simply the playground for the atom, where atom is moving around. But this is still a little bit similar, right? Because what is a Dirac? Where the electron is swimming around, like what was it? Gurame. Right? Like a gurame. Because it is QED vacuum, right? But QCD vacuum is similar, but unfortunately, in Dirac vacuum, photon interacts weakly with the electron because coupling constant is the fine structure constant, 1/137. But in the case of a QCD vacuum, gluons interact strongly with quarks. That's why QCD vacuum is so complicated. So we can only talk about the QCD vacuum mentioning the gluon condensate and also quark condensate. The gluon condensate and quark condensate, and also there are many different types of condensate, mixed condensate, the four-quark condensate, hybrid condensate. All the finite value of these condensates are simply properties of the QCD vacuum. I can tell you on in that way.
Actually, there are more questions. Maybe we will select one of them. How is it different from QED vacuum?
QED and QCD vacuum.
Yeah.
I just explained this. QED vacuum.
Yeah.
Simply, you see, you also have to be very careful. When you learn advanced quantum mechanics, you usually draw the diagram as I draw. That here, let me do self let me criticize myself. Yeah, this one. This one is, oops. This is schematic. This is really schematic diagram, mathematically incorrect. Because in quantum field theory, you cannot draw the line in this way. Right? This is what Dirac wrote in a quantum mechanical way. Okay? Quantum mechanically, it is very nice picture for the relativistic quantum mechanics. So QED vacuum means here, instead of the quarks, we have the electrons. Okay? So if one electron goes above, of course, in the QED vacuum, you don't have any mass gap. You have simply electron mass and electron mass, the 2MeC squared, this energy difference. Now, let's assume that one electron can hop into this space, then this can be free, but this can be hole, the electron, the real electron. But here somehow you have one hole. This is called hole. So when you learn, for example, semiconductors, this hole is very important. But this idea of the hole comes from this Dirac theory, from the QED vacuum. So that is QED vacuum. The QED vacuum can be handled, can be solved, because alpha, the Feinstein's constant, is rather small. So you can understand by using the quantum electrodynamics. But on the other hand, QCD vacuum is so difficult because of coupling constant. Maybe this is answered to that question.
Yeah, thank you very much. I think now time is almost 3 o'clock. Yeah, I think I have to close this session because it's 1 minute to 3 o'clock.
Yeah.
Let's give applause once again to
Thank you very much.
Professor Kim. Thank you very much for this. And we have the tradition to give you a certificate. Certificate is important here. We'll make a photo. Can be, yeah. So let me read this. Yeah, this certificate is awarded to Dr. Renat Hyun-Chul Kim. They didn't call you professor here, yeah. In recognition of a valuable contribution as speaker in the seminar on chiral effective theory for the structure of the nucleon. This is given by the Department of Physics. Thank you very much. Okay, thank you very much. Thank you very much. 감사합니다. Oke, dengan demikian saya tutup. Terima kasih atas perhatiannya ya. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore, salam sejahtera untuk kita semua. Terima kasih.